For 50 years, the master plan for Mars was uh, incredibly simple.
Mm.
I mean, almost dangerously so, when you really think about it.
Absolutely. It was essentially brute force.
Right. The idea was basically to just drop thermonuclear weapons over the Martian poles,
Yeah.
or, use these massive space mirrors to melt the ice caps.
Just add heat and weight.
Exactly. You release that frozen blanket of carbon dioxide trapped inside the ice, and you just sit back and watch the planet turn green. It was the ultimate science fiction dream.
The operative word there being fiction, right?
Yeah, exactly. Because in the summer of 2023, a single computer simulation run out of the University of Colorado pretty much proved that even if you melted every single ounce of ice on Mars with like 100% efficiency, you would barely change a thing.
It was a devastating realization for the community.
So devastating. I mean, picture this. If you stepped outside onto that newly warmed world after doing all that work, the atmospheric pressure would still be so low that your blood would literally boil in your veins within seconds.
Yeah. That simulation, it really is the ultimate demarcation line in our understanding of planetary science.
How so?
Well, in the history of how humanity conceptualizes our future in space, there's basically the era before the numbers, and then there's the incredibly sobering, uncompromising era after.
The era of reality.
Precisely. Because what that simulation demonstrated is that our whole intuition about planetary engineering is fundamentally flawed. We sort of assumed Mars was this sleeping giant that just needed a spark.
Right, the sleeping giant metaphor. We all thought it had this dense atmosphere locked away in the freezer, and we just needed to, pull the plug.
But the freezer was empty.
Yeah. And to really grasp the devastation of that 2023 data, we have to look at the baseline numbers. Like, for you listening, sitting in your room right now, the atmospheric pressure at sea level on Earth is roughly 1,013 millibars.
That's the physical weight of the air pushing down on your skin right now.
Yeah, right. But Mars currently, it sits at a functional vacuum of about 6 millibars. That is 0.6% of Earth's pressure.
Practically nothing.
Nothing. So the simulation asked, okay, if we vaporize the entire South Polar ice cap, which is mostly frozen CO2, how much air do we actually get?
And the result wasn't a dense, breathable atmosphere.
No. It raised the pressure from 6 millibars to roughly 12 millibars. You jump from 0.6% to like 1.2% of Earth's pressure.
And, at 12 millibars, you are still deep inside the physical parameters of a vacuum, at least as far as human biology is concerned.
So you can't just take off your helmet.
Oh, absolutely not. A full pressure suit is mandatory. A momentary breach in a visor seal means rapid decompression. You get abullism, which is the literal boiling of your body fluids, and immediate death.
There's no holding your breath for a minute.
No grace period whatsoever.
It's the ultimate reality check.
Yeah.
I mean, we spent decades drawing blueprints for this romantic terraformed second home, and a single spreadsheet just crashed the fantasy.
It really did.
So that's exactly where we are taking this deep dive today. We're unpacking a comprehensive breakdown of the reality of Mars, drawing from this vast body of analysis, including the perspectives outlined in the source text. The Red Ribbon. The Long Resurrection of Mars.
Which is such a grounded, honest text.
It is. We're abandoning the magical thinking today. We are going to explore the excruciating, awe-inspiring, mathematically rigorous reality of what it will actually take to build a living world from scratch.
Because the universe really does not care about our science fiction novels.
It absolutely does not. And the first casualty of that reality check is what they call the classical plan.
Right. Because once the magic bullet of just melting the poles is mathematically taken off the table, we are forced to look at the actual long-term recipe for planetary engineering.
Right. If Mars doesn't have a thick atmosphere waiting in the ice, we have to manufacture one.
From scratch.
From absolute scratch. So let's lay the groundwork for that, because before we get into the timeline of this classical plan, we have to grapple with the sheer, incomprehensible scale of the canvas we are working on.
The physical size of the problem.
Exactly. I mean, we look at Mars through telescopes or just as a little red dot in the sky, and our brains tend to shrink it down to, like, the size of a continent or a country.
Yeah, it's a known cognitive bias. Because Mars is roughly half the diameter of Earth, we just intuitively scale down the effort required to change it.
But here's the thing. Earth is a water world. 71% of our planet is covered by deep oceans.
And Mars is entirely dry.
Entirely.
Yeah.
So if you take every single landmass on Earth, Asia, Africa, North America, South America, Europe, Antarctica, Australia, every island in the Pacific, you squish them all together.
That total land area is exactly equal to the surface area of Mars.
Right. every square meter of dry land you have ever conceived of.
It's a staggering comparison when you really visualize it.
Picture this for a second, right? You are handed a limitless supply of genetically engineered grass seed and lichen. Your task is to physically walk across and landscape all of Russia.
Good luck with that alone.
Right. But then you have to cross the Himalayas and seed all of China. Then you take a boat to Africa and cross the Sahara, planting life in every single dune.
It just keeps going.
Then you traverse the Amazon rainforest, the Rocky Mountains, the freezing wastes of Antarctica, the Australian outback, every valley, every crater, every canyon.
That is the actual physical footprint of Mars.
We aren't building a city here or like diverting a river. We're attempting to renovate a continuous freezing desert the size of our entire habitable world.
Which is exactly why the timeline for the classical plan isn't measured in years or decades, but in deep time.
Yeah, so the engineers who clung to the terraforming dream after 2023 constructed this hypothetical four-phase roadmap.
A 10,000-year process.
10,000 years. And phase one alone, just the initial kickstart that occupies the entire first century.
Let's look at the mechanics of phase one, because the engineering sounds like something straight out of a Kardashev Type 2 civilization.
It's wild, because the first step isn't down in the dirt, it's up in orbit.
Right, the orbital mirrors.
The plan calls for the construction of these massive mirrors. But we aren't talking about space telescopes here. We're talking about massive, ultra-thin, reflective sails spanning tens of kilometers across.
Literally mirrors the size of major metropolitan cities.
And the physics of building a city-sized mirror in space are just daunting. You aren't just unfurling a giant sheet of aluminum foil.
No, because a structure that massive interacts with the solar wind and radiation pressure.
Photons actually push it, right?
Exactly. The photons from the sun actually impart momentum when they bounce off the mirror. So a mirror that large becomes an unintended solar sail, constantly being pushed out of its precise orbital alignment.
So you can't just park it and leave it.
Not at all. You need a vast network of automated thrusters and thousands of tons of propellant just for station keeping.
Just to keep it from blowing away.
Just to ensure the focal point remains perfectly targeted on the Martian South Pole.
And the whole goal of focusing all that light is to force whatever trapped CO2 does exist out of the ice.
Yeah.
But the mirrors are only half the battle.
Right, there's the surface operation.
Yeah, while the sky is basically burning the poles, the surface is crawling with an army of automated nuclear-powered factories. And their entire job is to pollute.
Intentionally polluting a pristine planet.
They are strip mining the Martian regolith, extracting carbon and churning out thousands of tons of pure black soot into the thin atmosphere.
It is a meticulously calculated climate disaster. By dispersing black soot into the atmospheric circulation patterns, the dust eventually settles back down onto the polar ice.
Which changes the albedo.
Precisely. Water ice and dry ice have a very high albedo, meaning they reflect most of the sunlight that hits them right back into space. By coating the poles in black soot, you drastically lower the albedo.
So the ice gets dark.
The ice gets dark, and it begins to absorb the sun's thermal energy rather than reflecting it.
You're basically trying to brute force a climate change feedback loop. But the reality of phase one is it's a really hard pill to swallow.
The ROI is terrible.
It's awful.
Yeah.
You spend an entire century building city-sized mirrors in the vacuum of space, managing the orbital mechanics, running massive automated pollution factories, and at the end of 100 years, the average global temperature on Mars has risen.
But not by much.
No, it's gone from a deeply lethal negative 60 degrees Celsius to a slightly less lethal negative 40 degrees Celsius.
It is a monumental expenditure of civilizational energy for a 20-degree shift.
100 years for 20 degrees.
But thermodynamically speaking, that shift is enough to trigger phase two, which spans from year 100 to year 500.
So this is where the chemistry really has to evolve, right?
Yeah.
Because soot and trace CO2 won't carry the runaway greenhouse effect far enough.
No, this is the era of the super greenhouse gases.
The perfluorocarbons, PFCs. Now, we constantly hear about carbon dioxide on Earth as the primary driver of climate change, but compared to a PFC, carbon dioxide is, like, incredibly weak.
It is an entirely different class of molecule. Greenhouse gases work by absorbing infrared radiation, basically the heat that is radiating off the planet's surface and trapping it in the atmosphere instead of letting it escape into space.
Right.
Carbon dioxide absorbs a fairly narrow band of that infrared spectrum. But perfluorocarbons, which are entirely synthetic molecules constructed of carbon and fluorine,
They catch way more.
way more. They absorb infrared energy across a massive, incredibly wide spectrum. Molecule for molecule, a PFC is roughly 10,000 times more potent at trapping heat than CO2.
10,000 times. That's insane. So you transition the automated factories from pumping out soot to synthesizing massive quantities of these perfluorocarbons from the trace elements in the dirt.
And this phase actually starts to show visual results.
Yeah, after 4 centuries of pumping these super gases into the sky, the atmospheric pressure finally thickens up to about 10% of Earth's pressure. You're hitting roughly 100 millibars.
And at the equator, something pretty wild happens.
Right, you reach the triple point of water. Let's break that down, because the triple point is such a bizarre concept in physics.
It is. Essentially, the physical state of water, whether it's solid ice, liquid water, or gaseous vapor, depends entirely on a delicate balance between temperature and atmospheric pressure.
So it's not just about heat.
Not at all. In the current near vacuum of Mars, liquid water cannot exist. If you take a block of ice and heat it up, it doesn't melt into a puddle, it sublimates.
It flashes directly from a solid block of ice into an invisible gas.
Exactly. It skips the liquid phase entirely because there is no air pressure pushing down on the molecules to hold them together in a liquid state.
But at 100 millibars of pressure, during the warmest part of a summer afternoon at the Martian equator, you cross a thermodynamic threshold.
The pressure is finally heavy enough to force the H2O molecules to remain clustered together as a fluid.
So you would literally see the first persistent liquid water pool on the surface of Mars in 3 billion years.
You would, but we're not talking about crystal clear mountain streams here.
Oh no. The soil is deeply salty and toxic. The pressure only allows for these thick, highly saline brines to briefly pool before the temperature drops at night and they just freeze solid again.
It's harsh, but it is liquid. And that liquid brine is the prerequisite for phase 3, the long haul.
Right, phase 3. This spans from year 500 to year 2000. This is the biological terraforming phase.
Yeah.
Because, I mean, you can't rely on factories forever. You need a self-replicating engine to change the atmospheric chemistry globally.
You have to deploy armies of genetically engineered cyanobacteria and extremophiles.
Now, regular Earth bacteria would just die instantly.
Oh, immediately. Mars lacks a thick ozone layer, meaning the surface is constantly bombarded by ultraviolet radiation from the sun.
UV radiation acts like a microscopic pair of scissors, right?
That's a great way to put it. It slices right through DNA strands, mutating and killing cellular life.
Though to survive, the biological payload would require heavy genetic modification, likely splicing in traits from Earth extremophiles.
Like Deinococcus radiodurans.
Right. A bacterium capable of surviving massive doses of radiation by rapidly repairing its own shattered DNA.
So you seed the equatorial brines with these ultra-resilient engineered bacteria, and their job is simple: perform photosynthesis.
They breathe in the thick CO2 and PFC-rich air, use the sunlight for energy, and excrete oxygen.
It is a slow, agonizingly gradual chemical conversion of an entire planet's surface.
1,500 years of just watching bacteria breathe. But over that time, you get this incredible visual indicator that the planet is changing. The sky changes color.
This is a really beautiful piece of atmospheric physics. Right now, the Martian sky is a rusty butterscotch color.
Because of the dust.
Right. The atmosphere is incredibly thin and choked with fine particles of red iron oxide dust. Those dust particles scattered the longer red wavelengths of sunlight.
But as the cyanobacteria do their work, pumping oxygen into the atmosphere and thickening the air mass, the physics of how light passes through the sky fundamentally shifts.
You get Rayleigh scattering.
Rayleigh scattering. The thicker gas molecules begin scattering the shorter blue wavelengths of sunlight across the sky. So after 2 millennia, the butterscotch sky fades, and an iconic pale blue sky emerges.
Which signals the arrival of phase 4, year 2000 to year 10,000.
The big one.
The big one. Over 8 millennia, the relentless biological engine of the bacteria finally pushes the atmospheric oxygen levels up to 15%.
Okay, let's pause on that because the physics here are wild. You've spent 10,000 years, you've built city-sized mirrors, pumped out synthetic supergases, altered the thermodynamic state of the planet, and seeded a global biosphere of engineered bacteria.
A monumental achievement.
The sky is blue. The air contains 15% oxygen, which is technically enough for human lungs to utilize. You step out of the airlock, take off your helmet, and your blood immediately boils.
This is the devastating caveat of the classical plan.
10,000 years of work.
I know. You have manufactured the right kind of air, but you haven't manufactured enough weight. After 10,000 years, the total mass of the atmosphere only provides roughly 300 millibars of pressure. That is zero point 0.3 atmospheres.
Which introduces the Armstrong limit.
Exactly. The boiling point of any fluid is directly tied to the atmospheric pressure pushing down on it. At sea level on Earth, water boils at 100 degrees Celsius.
But as pressure drops,
The boiling point drops. At 300 millibars on Mars, the ambient pressure is so weak that the boiling point of water drops below 37 degrees Celsius.
and 37 degrees Celsius is normal human body temperature.
So, the water in your saliva, the fluid coating your lungs, the water in your bloodstream, it all aggressively boils into a gas simply from the heat of your own body.
That's horrifying.
To survive in Phase 4, 10 millennia into this grand project, you cannot walk around in a t-shirt.
You need a mechanical counterpressure suit, not a big, puffy Apollo-style gas suit, because you don't actually need a mobile bubble of air to breathe. You just have an oxygen mask hooked up to a small compressor to force that 15% oxygen into your lungs.
But the suit itself?
Right, the suit itself has to be a heavily insulated, skin-tight, highly pressurized elastic garment. Its entire purpose is to physically squeeze your body,
Acting as artificial atmospheric pressure.
physically holding your tissues together so your fluids remain liquid. You'd look like a 1950s B-movie character.
It really underscores a terrifying truth. You can spend 10,000 years changing the color of the sky, but gravity and pressure are absolute masters of biology.
Oh, really are.
And if we look even deeper at the physics, the situation gets even more grim. Because creating that 300 millibar atmosphere is only half the battle. Keeping it there is the real war.
Right, because the atmosphere won't stay put. We've spent 100 centuries filling the bathtub, but the tub has a massive unpluggable leak.
A planetary scale leak.
Exactly. This brings us to what planetary scientists call the silent killer and the planetary sieve. And it all starts deep underground with the dead core.
If we connect this to the bigger picture, to understand why Mars is dead, we have to understand why Earth is alive. Earth has a churning, superheated liquid iron outer core.
As the Earth rotates, the Coriolis force turns that swirling liquid metal into a massive geodynamo.
That dynamo generates a powerful magnetic field that bursts out from the poles and envelopes our entire planet in an invisible shield called the magnetosphere.
And Mars had one of those. Billions of years ago, Mars had a liquid core, a magnetic field, thick air, and deep oceans.
But Mars is small. Because it lacks the sheer mass and radioactive insulating bulk of Earth, its core cooled rapidly. Roughly 3 billion years ago, the geodynamo seized up.
The core solidified.
The magnetic shield collapsed, and suddenly Mars was entirely naked to the solar wind.
The solar wind, which, we use the word wind, but that's a terrible analogy. It implies a gentle breeze of light.
It's anything but gentle.
The solar wind is a continuous, violent stream of highly charged plasma protons and electrons blasted out by the sun at an incomprehensible speed of 400 kilometers per second.
And without a magnetic shield to deflect that plasma, the solar wind slams directly into the upper atmosphere of Mars. The physical mechanics of this are brutal.
It causes a process called sputtering.
Sputtering. The high-energy solar particles crash into Martian atmospheric molecules like billiard balls, knocking them clean out of the planet's gravitational grip.
Stripping the air away.
Right now, in its current frozen state, Mars is losing about 100 grams of its atmosphere every single second.
Which, 100 grams a second seems negligible when the air is already functionally non-existent. But wait, if the atmosphere gets thicker, it actually absorbs more solar wind.
Yes, we're essentially creating a larger sail for the sun to catch.
That's brutal.
That is the cruel paradox of terraforming. Atmospheric physics dictate that a thicker, denser atmosphere extends further out in space. The boundary layer, the exobase, gets higher.
So a thick atmosphere absorbs exponentially more kinetic energy from the solar wind.
It heats up dramatically at the very top, and because the gas molecules are hot and highly energetic, they reach escape velocity much faster.
So the harder we work to build the atmosphere, the faster the sun rips it away. The math is staggering. Calculations show that if we magically gifted Mars a thick, one-atmosphere Earth normal pressure tomorrow, the sputtering effect of the solar wind would tear away several million tons of atmospheric gas every single year.
Millions of tons. It creates a Sisyphean nightmare. You would have to constantly, endlessly replenish millions of tons of gas just to tread water.
And if your terraforming factories break down.
Or if the sun enters a particularly violent cycle of coronal mass ejections, the entire planetary climate begins to slip backward into a vacuum. You are in a permanent, unwinnable war with the star at the center of the solar system.
Unless we build our own shield?
Yeah.
Which brings us to the megastructure. And I have to say, of all the proposals we're unpacking today, this one borders on the absurd.
It's definitely ambitious.
We have to stop the solar wind. So the theoretical solution is an artificial magnetosphere positioned out in deep space.
Specifically positioned at the Mars L1 Lagrange point.
Let's define the L1 point for everyone. In orbital mechanics, a Lagrange point is essentially a gravitational parking spot. The L1 point sits perfectly balanced on the invisible line between the Sun and Mars.
The gravitational pull of the Sun pulling an object inward is exactly canceled out by the gravitational pull of Mars pulling it outward.
So if you park a satellite there, it stays locked in position, constantly hovering directly between Mars and the solar wind.
Right. And the engineering proposal is to construct a massive superconducting electromagnetic coil at this L1 point.
The goal is to generate an artificial magnetic dipole field of about 1 to 2 Teslas. As the solar wind races toward Mars, it hits this artificial magnetic bubble first and is deflected around the planet.
Much like a boulder diverting the current of a rushing river, Mars sits safely in the magnetic wake.
But the scale of this boulder, we aren't talking about a satellite the size of a school bus. To generate a magnetic field wide enough to cast a shadow over an entire planet, the physical loop of superconducting cable would have to be larger in diameter than the planet Mars itself.
And the energy requirements are astronomical. To power a superconducting electromagnet of that magnitude, you would require the constant, uninterrupted electrical output of roughly 1,000 commercial nuclear reactors.
So what does this all mean? We're essentially trying to fill a bathtub with a massive leak, and our solution is to build a planet-sized umbrella in space powered by 1,000 nuclear plants, just to slow the leak.
It's an incredible thought experiment.
I mean, let's think about the logistics of that. You have to launch 1,000 nuclear reactors at a gravity well, assemble them in the absolute zero vacuum of space, manage the incomprehensible heat dissipation.
Because vacuum is a terrible conductor of heat.
Right, so those reactors would melt themselves without massive radiator panels spanning hundreds of square kilometers, and you have to maintain them flawlessly. If the power grid fails for even a day, the solar wind immediately begins flaying the atmosphere off the planet again.
But, it ultimately ignores the final insurmountable law of planetary physics.
The gravity problem.
Because even if you build 1,000 nuclear reactors, even if you string a planet-sized wire through the vacuum of space, even if you completely block the solar wind, Mars will still lose its atmosphere.
Mars is a sieve.
It is. The mass of Mars is only about 10% of Earth's mass. Its surface gravity is 38% of Earth's. That means its escape velocity is drastically lower.
So things just float away easier.
Even completely shielded from the solar wind, the natural thermodynamic behavior of gases means that the lighter molecules at the top of the atmosphere will simply vibrate fast enough to achieve escape velocity on their own.
It's called Jean's escape, right?
Yes, Jean's escape. A planet with 38% gravity simply does not have the gravitational muscle to hold on to a thick, warm, volatile atmosphere over geologic time. Mars is structurally incapable of holding its breath.
Okay, so we're fighting a leaky bathtub. We've spent millennia trying to plug the leak with planetary-scale electromagnets and nuclear reactors. But here's the true irony. Even if we could seal the leak, we arrive at the most embarrassing, fundamental roadblock of the entire endeavor.
We don't have the materials.
We do not have the water or the air to fill the tub in the first place. This brings us to the inventory crisis.
Because all the classical models assumed the raw materials were buried on Mars, waiting to be unleashed. The turning point in that assumption was the MAVEN spacecraft.
MAVEN, the Mars Atmosphere and Volatile Evolution mission. It arrived in Martian orbit in 2014, and by 2018, it delivered the data that quietly killed the terraforming dream.
MAVEN was built to take inventory. It measured the escape rate of the atmosphere, analyzed the isotopic ratios of the gases, and mapped the carbon trapped in the polar caps and the surface regolith.
And the final tally was definitive.
It was. The vast majority of the ancient Martian atmosphere didn't freeze into the ground. It was lost to deep space billions of years ago.
It's just gone.
Completely gone. The data showed that if you utilized unimaginable technology to mine every single accessible CO2 molecule left on the planet,
Like vaporizing the poles entirely.
vaporize the poles, drill into deep permafrost, and chemically bake the carbon out of every single carbonate rock on the surface of the planet, you would completely exhaust the planet's carbon inventory.
And what does exhausting the entire planetary inventory get us?
15 millibars of atmospheric pressure.
You start at 6 millibars, you add your hard-fought 15, and you max out at 21 millibars. That's it.
That's the cap.
Let's put 21 millibars into human terms. The source gives an incredible comparison. On Earth, at the summit of Mount Everest, the atmospheric pressure is roughly 330 millibars. That is the edge of human survivability. It's the death zone, where oxygen starvation rapidly degrades cellular function.
And 21 millibars isn't even close to the top of Everest.
No. 21 millibars is effectively the hard vacuum of the stratosphere. You have strip-mined an entire planet, processed its entire crust, and the atmosphere is still functionally invisible and entirely lethal.
And that is only the carbon dioxide crisis. The true terror of the inventory problem lies in the missing buffer gas. To create an Earth-like atmosphere, you cannot just pump out oxygen and carbon dioxide. You need nitrogen.
Right. Earth's atmosphere, the air filling the room you're sitting in right now listening to this, is 78% nitrogen. Oxygen is only 21%.
Nitrogen is the unsung hero of habitability. It is a highly stable, inert gas. It doesn't chemically react easily.
Its primary job is to provide bulk mass to the atmosphere, generating heavy atmospheric pressure without poisoning us or catching fire.
Right. If an atmosphere was composed of high concentrations of pure oxygen, it would be a catastrophic fire hazard. Every spark, every static shock would ignite anything remotely flammable.
We learned this tragically during the Apollo 1 fire.
Nitrogen dilutes the oxygen and stabilizes the world.
And Evan confirmed that Mars has virtually no nitrogen left. Barely a trace. So if we want an atmosphere, we have to import the buffer gas. We have to bring the nitrogen with us.
And the math here is where the scale goes from difficult to absurd.
The calculations show we would need to import roughly 2,000 trillion tons of nitrogen to Mars.
A number that defies human comprehension. 2 quadrillion tons of gas. Where in the solar system do you acquire that kind of mass?
There are only 2 viable nitrogen reservoirs. The first is Venus.
Venus has a massive, thick, nitrogen-rich atmosphere. But Venus is a literal hellscape. The surface temperature is 475 degrees Celsius, hot enough to melt lead.
The pressure is 90 times that of Earth, which would crush a nuclear submarine like a tin can.
And it rains sulfuric acid. Setting up a multi-trillion-ton gas extraction facility on the surface of Venus and then rocketing that gas out of Venus's massive gravity well requires materials and energy systems that simply violate the limits of known engineering.
Which leaves the outer solar system, specifically Titan.
Titan, Saturn's largest moon.
Titan is fascinating. It's essentially a frozen petrochemical factory. It has a massive, thick atmosphere that is 95% nitrogen. It has lakes of liquid methane. The inventory is there. The nitrogen is practically pooling on the surface.
But Titan orbits Saturn. It is roughly 1.2 billion kilometers away from Mars, depending on their orbital alignments.
Here's where it gets really interesting. We aren't just moving dirt. We're talking about setting up an interplanetary Amazon delivery route for gas.
Let's look at the orbital mechanics of that. You have to build massive automated gas freighters. You launch them from Mars, navigate the asteroid belt, perform complex orbital maneuvers, likely utilizing Jupiter for a gravitational slingshot, and eventually arrive at the Saturnian system.
You drop down into Titan's gravity well, scoop up millions of tons of liquid nitrogen, blast back out of Titan's gravity, and perform the transfer burn back to Mars.
Because of the vast distances and the required delta V, the change in velocity needed for these maneuvers, a single round trip on an optimal trajectory takes about a decade.
A 10-year round trip per freighter. And let's contextualize the payload. The largest supertankers on Earth's oceans today carry about 500,000 tons of cargo.
If you built a fleet of fusion-powered space freighters, each capable of hauling 1 million tons of liquid nitrogen,
A ship twice the size of our largest ocean vessels.
you would need 2 billion successful round trips to hit your 2,000 trillion ton quota.
2 billion decade-long cargo runs. The logistics are paralyzing. But let's indulge the fantasy. Let's say we have the 1,000 space reactors, the magnetic shield, the 2 billion fusion freighters. We strip mine Titan, we pressurize Mars, the sky is blue, the pressure is a comfortable atmosphere. We finally step outside, ready to plant a garden.
And we die anyway.
We die anyway, because the ground itself is toxic.
The perchlorate crisis. This is arguably the most insidious discovery we've made about the Martian surface. The dirt isn't just dead, it is chemically aggressive. Martian regolith is laced with high concentrations of chlorine salts called perchlorates.
And these aren't just an annoyance. Perchlorates are severely toxic to human biology. They are highly oxidized compounds.
If ingested or inhaled, they aggressively interfere with the human thyroid gland, blocking the uptake of iodine, which destabilizes your entire metabolic and endocrine system.
Breathing in fine perchlorate dust causes massive, irreversible lung damage.
And you cannot avoid it, because Mars is subject to global dust storms. Every few years, massive convection currents whip up the fine surface regolith and blanket the entire globe in a choking red haze.
Over the last 3 billion years, these global storms have meticulously distributed perchlorate salts evenly across the entire planet. They are in every dune, every crater floor, every canyon. So before you can plant a single potato, before you can safely touch the dirt without a hazmat suit, you have to literally wash a planet.
How do you bioremediate a continent-sized desert? You would have to deploy global fleets of autonomous rovers to literally wash the soil, extracting the perchlorates using chemical solvents, or deploy highly specialized engineered bacteria designed specifically to consume and neutralize chlorine compounds on a planetary scale.
You were talking about soil treatment infrastructure exceeding the industrial output of modern Earth, running constantly for centuries.
Which brings us to the ultimate enemy, the claw.
We've laid out the technological impossibilities, the missing gas, the dead core, the toxic soil, the low gravity. But the most profound barrier to terraforming Mars isn't a lack of fusion freighters or genetic engineering. The barrier is us. It is the deep time dilemma.
This raises an important question. Planetary engineering fundamentally outpaces the human attention span. The most optimistic models suggest that a global terraforming effort, from the first mirror to the first breathable breath, would take a minimum of 300,000 years.
300 millennia. We throw these numbers around, but let's anchor that to reality. Homo sapiens, anatomically modern humans, have only existed on Earth for roughly 300,000 years.
We are proposing a construction project that lasts as long as our species has existed.
Think about the sociological implications of that. The Great Pyramid of Giza took a couple of decades to build. The Great Wall of China took roughly 2,000 years, but that was intermittent, fractured by long periods of dynastic collapse.
No human institution, no government, no continuous physical project has ever outlasted the oldest living trees on Earth. A bristlecone pine can live for 5,000 years. Human empires rarely last 500.
We are a deeply volatile species. We have wars, we have economic collapses, we have ideological revolutions. How could we possibly maintain the institutional memory, the uninterrupted funding, and the absolute global consensus required to continuously manage a planetary climate system for 300,000 years?
Even language shifts so drastically over a few millennia that the engineers at the end of the project wouldn't be able to read the original blueprints without a translator.
And you cannot take a break. The terraforming process is not passive, it is highly unstable. If you lose focus, the planet actively tries to kill itself.
This is the runaway greenhouse risk.
We talked about warming the planet earlier, but warming a frozen world is a razor's edge. As you raise the global temperature, you start thawing out deep underground permafrost. Buried in that permafrost are vast deposits of methane clathrates.
Methane clathrates are essentially cages of ice that trap molecules of methane gas inside them. When the ice thaws, the methane is released into the atmosphere.
And methane is an incredibly aggressive greenhouse gas. Over a short time scale, it is roughly 80 times more potent at trapping heat than carbon dioxide.
So you warm the planet slightly, the permafrost thaws. Millions of tons of methane vent into the atmosphere. The methane aggressively traps more solar heat, causing the planet to warm even faster. That rapid warming thaws deeper permafrost, releasing exponentially more methane.
It's a positive feedback loop. On Earth, a runaway greenhouse effect from melting permafrost is our greatest fear. It's the tipping point we are terrified of crossing. But on Mars, initiating a runaway greenhouse effect is the actual engine of terraforming. It's how you do it.
It's like trying to start a controlled forest fire to warm your house.
Exactly. And controlling a fire of that magnitude requires a climate engineering network that defies belief.
If the warming accelerates too quickly, you need to be able to instantly deploy massive orbital sunshades to block the sun and cool the planet down. You need gargantuan atmospheric processors on the surface capable of scrubbing millions of tons of excess greenhouse gases out of the air in real time.
You're manually piloting the climate of an entire world. And what happens if the pilot blinks? What happens if there's a world war back on Earth, the supply lines are cut, and the orbital sunshades fail to deploy?
Or if 1 century a political faction simply decides they're tired of funding the atmospheric scrubbers. The margin for error is absolute zero.
One failure.
One failure, one war, or 1 century of negligence, and the planet tips into one of two extremes. Either the feedback loop breaks, the atmosphere cools, and all that hard-earned gas freezes out, falling back to the surface as dry ice snow, returning the planet to a snowball state.
Or worse, it backfires entirely. The Venus scenario.
Precisely. The methane release runs totally out of control. The equatorial temperatures soar to 150 degrees Celsius. Whatever oceans you've managed to build aggressively boil away into vapor, adding water vapor, which is also a greenhouse gas to the mix.
The heat triggers massive volcanic outgassing, filling the sky with sulfur dioxide.
You don't create Earth 2.0, you accidentally create a toxic, boiling hothouse with sulfuric acid rain.
It is a devastating realization. If global terraforming requires magical technology, 2 billion freighters, and 300,000 years of unbroken sociological perfection, we have to admit defeat. Global terraforming is a fantasy.
But that doesn't mean Mars remains empty, because there is a highly realistic, infinitely more pragmatic alternative. If we can't change the entire planet, we enclose pieces of it.
Paraterraforming is the pivot from grand planetary engineering to highly localized architecture. We stop fighting the sheer scale of Mars, and we start utilizing its unique geography to our advantage.
And a crown jewel of Martian geography is Valles Marineris.
This is the Grand Canyon of Mars, but calling it a canyon is almost an insult to its scale. Valles Marineris is an immense tectonic crack spanning 4,000 kilometers across the Martian equator. It is up to 200 kilometers wide in places.
But the most important metric is its depth. The canyon plunges up to 7 kilometers deep.
7 kilometers straight down into the crust. The concept of paraterraforming suggests we don't try to build an atmosphere up into space. Instead, we use the canyon as a bowl, and we put a roof over it.
You take the Martian dirt, which is incredibly rich in silica. You deploy massive automated smelters to refine it, and you manufacture millions of tons of high-tensile, transparent Martian glass.
And you weave a continuous transparent roof across the 200-kilometer width of the canyon, sealing it off from the vacuum above.
Now, the brilliant physics here isn't just that you have an enclosed space. The genius relies on the barometric formula.
Let's explain how the barometric formula makes this work, because this is the cleverest physics trick in the entire concept.
Atmospheric pressure isn't just about how much gas you have, it's about gravity compressing that gas. As you go deeper into a gravity well, the weight of the air above pushes down on the air below, compressing it and creating higher pressure at the bottom.
Just like swimming to the bottom of a pool, the deeper you go, the heavier the water above you feels on your eardrums.
Exactly. Because Valles Marineris is 7 kilometers deep, you only need to pump a relatively small amount of gas, nitrogen, and oxygen imported by a much smaller, manageable shipments into the sealed canyon.
By the time that gas column reaches the floor of the canyon, 7 kilometers down, the sheer physical weight of the gas above it compresses it naturally.
At the canyon floor, you achieve nearly 1 full atmosphere of pressure, Earth normal pressure.
Without a global magnetic shield, without 1,000 nuclear reactors, without a 300,000-year wait, down on the floor of that sealed canyon, you don't need the mechanical counterpressure suit.
You don't need the oxygen mask.
You step out of your habitat wearing a t-shirt and you breathe normal air. You can plant vast, towering pine forests that stretch hundreds of meters up into the canyon. You have an indoor, canyon-sized terrarium spanning 4,000 kilometers. I absolutely love this idea.
And the canyon itself provides the protection the planet lacks. The sheer 7-kilometer-high rock walls naturally absorb and block the vast majority of incoming galactic cosmic radiation and solar flares.
The walls themselves are layered with ancient glaciers and aquifers, providing a massive, easily accessible reservoir of water right inside the habitat.
It's an incredibly elegant solution, and compared to the deep time dilemma of global terraforming, paraterraforming is rapid. A massive canyon dome project could theoretically be constructed in 500 years, eventually housing millions of people.
And because of this realization, the models actually provide us with a highly realistic century-by-century timeline of human history on Mars. Let's walk through that timeline.
The timeline strips away the fantasy and gives us the gritty, pragmatic roadmap. From 2040 to roughly 2100, the focus is purely on brutal survival.
Right, there are no glass domes yet. The surface is simply too lethal. The radiation environment is unforgiving. So the first true Martian cities aren't built on the surface. They were built underground, inside ancient, naturally occurring lava tubes.
These deep basalt caves provide perfect, immediate shielding from cosmic rays and solar proton events. For the first century, we are troglodytes.
Moving into the 22nd century, 2100 to 2200 humanity establishes a firmer industrial foothold. This is the era of localized experimentation. We begin smelting steel and glass.
We attempt small-scale biological deployments, releasing engineered extremophile lichen into the bottoms of deep craters, purely to test the absolute limits of their survival against the cold and UV radiation.
And we acknowledge failure. The lichen inevitably die. The ambient conditions outside the airlocks remain absolutely uncompromising. But the data from those localized failures allows us to refine our materials, leading into the era of 2200 to 2500, the first true domed craters.
We select a small, 100-kilometer wide crater. We seal it with a manufactured dome, import the necessary nitrogen buffer gas, regulate the internal temperature, and introduce a closed-loop biosphere.
And inside that specific, isolated crater, the monumental shift occurs. A human being finally walks outside without a pressure suit. Inside that 100-kilometer bubble, liquid water pools on the surface for the first time in over 3 billion years, remaining fluid, not sublimating away.
It is a tiny jewel of life, but outside the glass, a millimeter away, the planet remains a freezing, irradiated vacuum.
Which culminates in the deep future, the years 4,000 to 10,000. The crater network has proven successful, the population of Mars numbers in the millions, the industrial capacity is vast, and this is when the true generational project begins. The roofing of Valles Marineris.
I love thinking about the psychology of this era. It takes generations just to construct the roof over the canyon. You have entire generations of humans born inside lava tubes or small crater domes.
They work their entire adult lives assembling massive glass panels over the abyss of the canyon. They grow old and die, knowing they will never see the project finished, never feel the wind of the canyon forest.
It's the ultimate cathedral building mindset, but on an interplanetary scale.
And by the time the canyon is sealed and the forests are grown, the people living there are no longer Earthlings. Earth to them is a museum planet, a high-gravity, incredibly wet, bizarrely chaotic world of open skies and uncontained weather.
They're fully, culturally, and biologically Martian.
Which leads to the final, almost poignant era of the timeline, 10,000 to 100,000 years into the future. You'd think, living in a 4,000-kilometer-long paradise inside a canyon, we would be satisfied. But humans are restless.
The dream of global terraforming never truly dies, it simply goes dormant. The historical model suggests that every few centuries, a new generation of Martian scientists and ambitious politicians will look up through the glass roof of the canyon at the rusty sky and ask the old question, what if we try again?
They argue that technology has advanced, they have stable fusion power now, they have nanotechnological swarms capable of atmospheric processing. They redraw the blueprints for the artificial magnetic shield at the L1 point. They propose restarting the 300,000-year clock.
But the underlying physics and the sociology remain unchanged. When they run the advanced simulations, the answer is exactly the same as the University of Colorado simulation from 2023.
The energy cost is too high.
The planetary sieve is too porous. The civilizational commitment of hundreds of thousands of years is too fragile.
So they debate it. They acknowledge the staggering hubris of trying to fight the solar wind. They reject global terraforming once again. And they simply go find another deep crater and build another dome.
It perfectly encapsulates the final thesis of the source material, the final honesty.
Yeah, that terraforming isn't an engineering problem, it's a civilizational one.
To fundamentally rewrite the thermodynamic state of a planet, you require a society that is completely stable, immensely wealthy, entirely unified, and capable of unbroken multi-millennial focus. You need a species that refuses to succumb to its own internal volatility. And humans, fundamentally, are not that species. We are builders of domes, not architects of stars.
But there is a beautiful, deeply profound way to look at this reality, rather than viewing it as a failure. The text calls it the theology of resurrection. Look up at that little red dot in the sky. Every atom of iron oxide was once water rock chemistry.
The rust is the fossilized footprint of an ancient wet world.
We aren't trying to force Mars to become Earth. Earth already exists. We're trying to see if a dead world can be resurrected, to see if the clock can be wound backward. And resurrecting a world isn't an act of brute force engineering. It's an act of theology, not just engineering.
It requires deep time.
And that leaves you with one final, lingering thought to mull over, long after this deep dive is done. We know that to survive on Mars, to endure the lethal radiation, to build those lava tube cities, to cooperate flawlessly over generations, just to put a glass roof over a canyon, Humanity will be forced to develop an unbreakable patience and a level of absolute global cooperation we have never achieved on Earth.
The environment will demand it.
Exactly. So the question is, 10 or 20,000 years from now, when the roof over Valles Marineris finally closes, will the humans who live inside it even be recognizable to us? Not just culturally, but biologically, with a lower gravity altering their bone density, the enclosed environments shaping their immune systems, and the absolute necessity of intense cooperative survival shaping their sociology. Will the brutal, uncompromising civ of Mars be the very crucible that forcibly evolves us into a completely different, fundamentally wiser species?